Hello everyone, good morning. Welcome back to the class ECE317, the digital signal processing. This is the second class. Last time we go over the syllabus and give some introduction, and we also discuss what is a signal and how to describe a signal. And today we will consider some more details. We will study some useful signals, how to represent them, and how they looks like, and how it looks like. And before the class, I think I want to talk a little bit about the lab, because some students ask me when the lab will start and something else related with the lab. So here, this is a blackboard. You go to the blackboard, you go to our class ECE317. Then here I have a lab material. So you click on it, then you will see here's a folder named lab manuals, and I have explained here. The first lab will start in the third week of the semester, and you need to read the instruction before you start the lab. If there are some requirement for the pre-lab, you need to finish the pre-lab before you attend the lab. And the lab menu, click on it. Actually the first lab is labeled as lab 00. It's just very basic things, so I use 00. So this is the lab in the third week, the first lab, right? In the third week, it will be this one. All right, and the report of this lab will be submitted in the fourth week. So the third week you do lab 00 and submit it in the fourth week, and in fourth week you start lab 01 and you will submit a report in the fifth week, and so on. All right. Okay, this is a lab. Now let's go back to our class. And what else? Oh yeah, for the homework. So today we will have the first homework assignment. After the class, I will give the first homework. This homework will cover the first 2 weeks, and it will due on the third week Wednesday. All right. Yeah. The first 2 weeks we do not have any homework due, but we have homework. They were due on the third week Wednesday. All right. This is a ECE317. This is second class. Okay, so we want to study some special signals. The first one is the signals. Okay, signals. The first one is a unit impulse. We denote it as delta of n. So its value will be 1 or 0. When it is 1, that means n is 0. Only when n is 0, delta has value 1. And for all the other n's, the value of delta is 0. Okay, so this is a impulse, unit impulse. This is 1, the unit impulse. We can use graph, right? You can see in a graph. This side is n, this axis is n, and here's the delta. And when n is 0, we have value 1. And then all the other values for all the other n's, n equal to 0, 1, 2, 3, 4, and negative 1, negative 2, and so on. All these values, they are 0. You can also list as like delta equal to the infinite values, right? The 0, the 1, the 0 again, 0, like this. And you need to indicate here n is 0. Right? N is 0. So this is unit impulse. We use it a lot.
And the second signal is a unit step. Unit step signal. It is U of n. U of n. Its value, okay, U also have only 1 and 0 as its values. And okay, for which case U have value 1, that is n larger than or equal to 0. And for negative n, its value is 0. And we can also have a graph. So here, when n is positive or 0, when n is positive or 0, then U of n is 1, 1, 1, always 1 in this side, always 1, always 1. It's a U of n. And for negative n, it is always 0, always 0, 0. So this is a U of n. It's a step, right? You see, it's 0, then coming up to be 1, then keep 1. This is step, unit step. Yeah, as its name. And the delta is also impulse, right? It's a 0, then come up to 1, then go back to 0. So this is an impulse. This is impulse. I think you should also know the similar signals for continuous time signal, right? Yeah. But here we study the discrete time signal, so it looks like this. All right. This is first one, the second one. For these two signals, they have a kind of relation. Yeah, I need some operations on signal, so that will be next time. So today you know, okay, this is delta, this is U, that will be fine. And other than these two, we also have more signals. We have the exponential, not exponential power, just power, kind of power signals. So this is third one. It says I just use X, no special notation for this kind of signal. It is just A to the n. A to the n. A is a constant. A is a constant. A is a constant. So this is power of A. Power of A. And the fourth one, it is still A to the n, but I times the unit step. So this is the, we only needed the positive side of the power. The negative side, because when n is negative, U of n is 0, right? Yeah, we just have this. U of n, when n is negative, this is 0. So U of n times this one, when n is negative, this is 0. 0 times n is still 0. So this x of n in negative side is 0. The positive side is the same with that one. Okay. Then the fifth one, we have x of n, which is a cosine some omega 0 n. Okay, this is a sinusoid, cosine signal, right? Cosine wave. And similar, we have x n equal to sine omega 0 n. And more general, we can have x of n equal to a cosine omega 0 n plus theta 0. So all these are the sine waves or cosine waves. And then we can have a combined version, the complex number version of the sinusoid. So I say this is a 6. It's a x of n equal to some a times e to the j omega 0 n. Maybe say, yeah, plus theta 0. Like this. Alright. And okay, actually this is special case of 3, and here I say a is a real number. And we can have this is the seventh signal, x of n equal to, okay, now this I will say a is a complex number. A is a complex number. So I will say e to the no, still a to the n, but a complex number. Okay, most common used signals. They are most common used signals, and in general, if you have a combination of them, they are also kind of signal, right? But they are these things like you can build a signal by them. Then how do they look like? Yeah, I just write a formula here. I didn't show give a graph or find the values, because that need a lot of calculation, you see, right? A to the n for different n, different a, right? A lot of value, cosine or sine, and different omega 0. So I will do this by computer. Okay. Yeah. Now let's go to the computer. I have opened the MATLAB here. I will use MATLAB to go over these signals. We look at the first one. So first one is x of n, which is a to the n. Here a real number. Actually, we have three cases. How to say? If you want, you can give more cases. A equal to 0, equal to 1, negative 1, and a positive or a negative, and larger than 1, smaller than 1, right? So you can consider a in different cases. For these three cases, they are special value. If a is 0, then x is always 0, right? This is just 0, nothing. If a is 1, then this is always 1, right? Always 1. If it is negative 1, then it will be jumped alternatively. This is 1, negative 1. When n is 0, this is 1, then negative 1, then 1, then negative 1, then 1, right? The power of negative 1. So it's changing from 1 to negative 1, 1 to negative 1. Okay, so these are special cases. Then we consider here for positive a and negative a. For positive a and negative a. For a larger than 1 or smaller than 1. That's the value. Larger than 1, smaller than 1. So actually here we have four cases, right? So a positive, a negative, a larger than 1, absolute value, a smaller than 1. So we have four cases, right? Four cases. Now let's look at these four cases. Go to MATLAB. Alright, here. Now we start with n. N we can choose from like a negative 3 to positive 5. Yeah, any integers. I give a list of integers. And then let's see what are the values of x of n. X of n actually is some a to the power. And what is a? I can choose like 2 to the n. Right, a is 2. A is 2. Oh, I need a dot here. It's a dot and that triangle, that arrow. That means the power, here is a vector, right? N is a vector, so this is the power, but you need a vector here. Alright, so this is the x. You see, we have the value of x. But if you just look at this, it's not so clearly, right? A list of numbers. Alright, we can use a graph. So you can use, we have different functions. We can use plot or stem of x, and n and x. Okay. Alright, we have the graph looks like this. You see, this axis is n. So I put n here. and run from -3 to 5, and x its value were between 0 to, actually depending on, this will be 16, 32 is here, the logic value is here, 32, right? So this is a power of 2. If you use a curve, you can also use plot n and x. So by this way you have a curve. It's a curve. Yeah. You can use either. Then you can see how it looks like. This is a is positive, right? The signal is increasing, and you can also have -1. X is -2. -2 with the power, and we use them again. So how do it look like? Oh, okay, it's here. It's a value will be positive, negative, positive, negative, positive, negative, positive, like this, right? Yeah. If you use plot, I use a circle to see the value. Okay. Oh, the plot no curve. Sorry. Now just like this way, you can have a curve. It's here. It's here. Up and down, the signal look like this. When n is increasing, now I already calculated n until 5, right? If you have more, then you can have more values. The n is here. N is 3 to 5. If, for example, I use 15, n is -3 to 15. Then I still calculate x as a power of it, and this is -2, yeah. And then plot it, stamp it. Oh, it looks similar. The same is just you change the unit, right? Here you see the unit is 2 times 10 to the 4th. 10 to the 4th is what? 10 to the 4th, or this is 10,000. It's 20,000. The scale is 10,000. That's too much. Yeah, it's 15. The power is a power, right? Yeah. If you want, you can now use 2. You use 1.2. That will be not so much. That's not. Yeah, this is 1.2. It's still increasing, but you see the scale is until the largest value is around positive 15 or negative 20, something like that. Yeah, it's not too large. Every time increase by 2%, 20%, increasing like this. So this is the power of A. While A is larger than 1. Positive or negative, larger than 1. And if smaller than 1, look here, smaller than 1, dot 8, like this, what I happen? Okay, now the value will tend to be smaller and smaller, right? Smaller and smaller. Here A is negative, so by power the value will be positive, then negative, positive, and negative. It will switch from up and down, right? Every value. If they are positive, then they will keep in one side, in the positive side. If I remove this negative and remove this negative, then the graph will look like this. Okay, it's always in positive side. Right? Okay, so this is the signal for A to the N. And second one, we times this A to the N with a U of N. We times this. You this is a force. X of n is a to the n times u of n. So this one will look like in the positive n it is a to the n. In negative n it will be 0. Alright, so we can see here. I show you that a, right? I already have x. Now I use a u. U is a unit step. So u is, we just consider n larger than or equal to 0. So this is a logic operation, right? This is logic operation. When the logic is true, this operation will return 1, right? The true is 1, and when it fails, it will return 0. So we use this way, I get the answer will be 0 or 1. When u larger than or equal to 0, when n is larger than or equal to 0, the value of u are 1s, or these are 1s. And when n is negative, they're 0, right? So I have u, and I let u times that x. I use y for it. Okay, y equal to x times u. But now they are vectors, so they are list of values like this, dot times. So they will multiply element by element. Okay, we get this one. We can plot a stem to see how it looks like. Now it's stem y, right? Y is multiplied by this unit step. Oh, you see, looks like this. In the negative n, right? For n equal to -4, 3, 2, -1, the value are 0. So here we have 0 value. And for positive n or 0, when n is 0 or positive, its value, okay, that will be this. That will be this. So the things like it cut off the negative side. Okay. Yeah. And we can use different a. This a is smaller than 1 and then smaller than 1 and then positive. You can use a negative. This is x. Then y is still x times u. Then stem y. Yeah, looks like this. Right. Positive, negative, positive, negative. And if we have a is larger than 1, I put 1, 1. Oh, no, 1, 2. Larger than 1. This is negative and larger than 1. And positive. Okay, we try for positive first. Positive and negative. And larger than a is positive and negative is larger than 1 and positive. And the y is still with a u. Then you can see how it looks like. Okay, so this is a similar thing, right? You cut off one side, cut off the negative side, and only keep the positive values. Okay, so this is a third case, or fourth case. Then next one. Okay, this one we consider cosine and the sine. Yeah, these should be waveforms, right? Waveforms. And this you with a more complex case is a times cosine with frequency and phase. Right? Yeah. Okay. So here I can still use the same n, right? N can be same, but x is changing. I use different x. Now x is some capital A. For example, I use 3 for the capital A times the cosine of omega 0. What is omega 0? Like 0.4, whatever, right? Omega 0 times n. Okay, now is a dot. I need a dot here, right? Because n is a vector. So So 0.4 times n, that means 0.4 times all element of n, every element of n. And yeah, now I just more generally, I give a phase. What is a phase? Phase is pi over 5, for example. Okay, now I have x. How it looks like? Of course, it will be a waveform, right? Stem n and x. It looks like this. It's a waveform, right? It's a cosine with certain phase. So when n0 here, when n0, this value is not 1 because I have a phase. Then up and down, it's a waveform. If we give more n's, now n is 15, right? I get like 45, 3 times. Okay, we have more n's. Then I have x in the same way, and step to see how it looks like. Oh, we have a lot, right? We have a lot. So this is a sine or cosine. Doesn't matter because it's just cosine. You can think it's a cosine, right? Shifted one. All right. But here we have one thing. Is this a periodic signal? You see, you think this is a period, right? One negative side, one positive side, then another negative side, then positive side, then negative side, then positive side, right? So are they periodically? I would say yes or no. You see, here, this one, the first negative peak, and then followed by positive peak, right? The first value is here. This is the first value of this period. You got it? And here, this is the first value of next period. And here is the first value of the other period, right? So we discussed 3 periods. Here, this negative and this positive, this is 1 period. Another negative part and a positive part, second period. Another negative part and, yeah, they only half. This is another period, right? But the first value, you look at the first value, this one, they are different. Are they periodically? No. So here's a very important difference between continuous time signal and discrete time signal. In discrete time case, a sinusoid signal might be not period, maybe not periodic. You can't find period. Like this one is not period. It will not repeat. It is not, the waveform is repeat, but you only take several values from each period, right? So different period, you may take different point. So your values will not repeat. So in like this one, the first period you have this value, the next period you get this one. It's different. You got it? Yeah, so you have to pay attention. Only if in every period you take the same value. So what is the case? Let me write it down here. Okay, this is for the sine signal and cosine signals. Fine. I just write down the most general form. This is A times cosine omega 0 n plus theta 0. This one. It is a waveform. Right? It is a wave. Something looks like. Yeah, looks like this. You have the value, not the curve, just those dots. Those dots are the values in the signal. Right, in signal. You have this. But it will be not a periodic signal in general. Generally, it is not periodic. All right. For only when omega 0 equal to 2 pi times some k over some f, it is periodic. This is the case. You can have the every n. This is a symbol, right? You take symbol, not some. Yeah, you later we should know this kind of you take symbol from sine wave or cosine wave, right? So when this omega 0 is 2 pi times integer divided by integer, then the signal can repeat. You can have same point that you have same value for the same point. We can have a look. Like here, I have x equal to this one, right? This is 0.4. I use not 0.4. I use pi over. For example, I use pi over 5. Not 5. Not 5 used. I use 7. Pi over 7 times n. This is different x, different omega 0. I have different x, and we can see how it looks like. Stem of these x. Okay, this time it is periodic. You see this value, this one, they are same. Here's the another value. It's just graph, which will be same. Yeah, you look at it. Maybe you have some error. Then you can list the value. You can see the list of the value. Here's x, right? X is here. You can see the values. I double click on it. I see the values. So I have 2.2592. Then some positive, some negative. Okay, the 15 number. You see. This one 2.2592. 2.2592. They're exact same, right? And next is 2.8919. Here's a 2.8919. Right? So you see every the period should be 15, right? The first number and 15 number they are same, or 14. Yeah. 15 is the next period. So 14. From 1 to 14 is one period, and then 15 should be 28. To 28 should be the next value. Right? I go to it. 28. Okay. 15 is here. Then 28. The 29. Next is 29. 29 will be next period, right? 29 according to 15. 29 and 15 are same. So they are the first value of one period, one cycle, right? 2.5, 2.25, 2.25. Yeah, they are same. So every 14 is one period. And yeah. And actually here it doesn't matter what is the theta. If you change the theta, the period will be same. Like I have x theta is pi over 5, right? If I change the phase angle to be pi over 5 and times 3, okay. I times 3 on it, then I have a larger phase angle, right? This is x, the new x, different x. And we can see how it looks like. That is. And it's similar, right? Still some waveform, just the phase different, and it's also periodic. You can check the value in this here list. It's still like 15 is 25753. When n is 15, its value is this one, and when n is 29, the value is this one, same. So still use 14 as a period. Every 14 is a period. Right? Okay. Let me put this see in the notes. We have a note. Omega 0 is how many pi? I forgot. Sorry. Is a pi over 7. A pi over 7. Then the period is, we use capital N for the period. It is 14. That means x of n plus 14 were equal to, sorry, it's here. I go to here, right? Now we have example. We have omega is a pi over 7, right? Omega 0 is pi over 7. Then the period is n equal to 14. That means x of n plus 14 equal to x of n. Yeah, x of n. So this is a periodic signal. This one is a periodic signal. But when omega 0 cannot write in this way, it is not periodic signal. Yeah, this is a somehow is different. Somehow different. Here, I use MATLAB. I use computer to find the period. Right? You can also use a calculator to find the period. A cosine omega 0 n plus theta 0 for omega 0 equal to pi over 7. How to find the period? We can work like this. So period, that means cosine omega 0 n plus theta 0 equal to cosine omega 0 n plus the period, right? The n change to be n plus the period plus sigma 0. Cosine, you want the cosine equal to another cosine. Yeah, we have a lot of cases, right? But here, because n is changing, you will think 2 pi, then no matter how to change, 2 pi always work, right? The cosine value, like this is cosine, right? Cosine value, like here, this one, they have same value, but the relation, you check the time, check the n, might be complex. But every 2 pi, that is normally it is a repeat every 2 pi. So here we just think this is 2 pi. So omega 0 times n, right? The difference, it will be 2 pi or 2 pi times sometimes the 2 times of 2 pi, 4 times of 2 pi, things like that. Now we have omega 0. We plug in what is the omega 0. We have omega 0 is pi over 7. So omega 0 n equal to pi over 7 times n. This one will equal to 2 pi or 4 pi or maybe negative 4 pi. You have a lot, right? You list here. So you can see how to make it is to be an integer. So pi divided, right? Pi cancel. This 7 move to the other side. It's just time. So n equal to 2 times 7 or 14. Or this is 4 pi. Then there will be 28 or negative 28 and so on. Okay, you can choose the smallest one among them. That will be this one. So period is 14. Period is 14. You can always find the period, right? And we can try more. If omega 0 is like a 2 over 5 pi, what will be period? Similar thing. We want omega 0 times n now is 2 over 5 pi, this is omega 0, times n. We want this equal to 2 pi or positive negative 2 times 2 pi positive negative 3 times 2 pi, and so on, right? Then we do some calculation. We cancel all the pi's and times 5 to the other side. Also cancel 2. I cancel 2 pi and times n to that side. So n equal to 2 pi cancel. So this is 5. Positive negative 10, positive negative 15, and so on. So this is period. So you can get 5 as a period. Got it? Yeah, we can also have a look in the MATLAB. If now x is period, the frequency, we still call it as frequency. The frequency is 2 pi over 5. 2 pi over 5. Then how it looks like? Oh, looks like this. Looks like this. Now what is the period? You can see we have 2 positive, then 3 negative. 2 positive, 3 negative, right? The values 2 positive, then 3 negative, then 2 positive, 3 negative. So every 5 values it will repeat. So the period is 5. The problem, right? Same with us. Can you see both? Yeah, I can. This way. Oh, this one I can only see the whole thing, the figure. Yes, here. So the period is 5. See, you can also find the period by the graph. You know, every 5 values it will repeat. Then what is the continuous case signal? You can have a look at the same time. So here this is x equal to n. Okay, I use a t. T equal to n is from negative 3, right? T also from negative 3 to 15 to 45. But I use a step 0.05 as a step to 45. Okay, this is a continuous time, another continuous time. For this time, I have another x, I say xc, continuous version of c. Continuous version of c, of x, continuous version of x, xc, it is now times t. Okay, I have xc. Yeah, I have xc, and I plotted figure 1. I need to hold on, and the stamp now is a t and xc. So I put 2 graphs together. Oh, I cannot use stamp. Sorry. Stamp is too much. There's a curve. There's a plot. So plot xn. Okay. Sorry. Up here. Stamp x and plot xc. I need a stamp x. Stamp n and x. This is step. Okay, and then I hold on. Then plot t and xc. Okay, this time I have 2 together. Yeah, things like this. Alright, so this curve is a continuous signal, and these stars, they are symbols. Yeah, you can think they are symbols of a continuous signal, that is discrete time signal. Things look like this. This looks like what? Some ghost here. Sorry. Yeah. Okay. That's all for today. Actually, I didn't finish, right? We have more signals, then we can discuss next time. Here I already finish these cosine things. We also have the complex version signals, so that will be next time. All right. Okay. Bye bye. See you next time.